Okay, so what we want to take a look at now is I want to analyze the situation, give us a problem involving high jump, and we're going to use this occasion to derive a fourth sort of starting equation over here. To go along with our other constant acceleration equations. Remember, only two of these equations are independent of each other. So any two of them are independent. And so the third one and the fourth one to be derived shortly can be derived from using algebra combining any of the other two. In this problem, what we have is we want to find out what is the launch speed of the center of mass of an Olympic class high jumper. And when you take a look at high jump records and the heights of high jumpers and so on, when you watch the high jump, they go from being not quite standing straight up, a little bit crutched with a big run, and then they go over the bar almost horizontal. And when they do that, this makes it so the center of mass of their body, like if you average the positions of all of the bits of matter in their body, it's located somewhere roughly near the top of your pelvis. It sort of varies depending upon the person, and there's a little bit of gender association with how high or low it sits on average, but in that ballpark. And what that means is that you don't have to get your feet to have the same force going up. It's about getting the center of your body up a shorter distance. You can have like a boost. You don't have to move your whole body up that height. You just have to move the lower parts have to move all closer to that height. Your head doesn't have to move as much at all. So we want to know, well, if the maximum height is that high, what is the launch speed, not of our feet, because that's more complicated, but of the center of mass of our body? We're modeling in all of these problems, we're acting as if all of the objects we've been talking about have all their mass concentrated into a zero-dimensional point. And that's located at the center of mass of an object. So if we were just talking about a ball, then it would be dead center of the ball. It's a uniform density ball. Person, again, somewhere in the pelvis area, probably upper pelvis area, more or less. And anyway, so I've drawn and labeled some things, but we haven't said everything here. First off, part of the physics involved here is that it's constant acceleration and it's free fall. So that means that our acceleration is going to be negative 9.8 meters per second squared. Our acceleration gets to be down, and I'm choosing up to be positive, down to be negative in this problem. When you get to your highest point, you got to think about what that means. You throw something like a pen up in the air. As it goes up, the acceleration from gravity is causing it to lose about 10 meters per second with each passing second. So that if we were taking a table here with time in seconds and velocity in meters per second, and we say g is about 10 meters per second squared, and we started off at 30 meters per second, then every second passing we would lose 10 meters per second. If up is positive and down is negative, you're going upward as long as these numbers are positive, as long as they're above 0. And you're going downward as long as they're negative and below 0. The point where it transitions from going upward to downward is the point where the numbers transition from positive to negative, when it's 0 velocity. So the velocity up here at our maximum height, which I'm going to call final velocity, is 0 meters per second. Now I want to call our attention to something else here. At that 0 velocity point, you still have acceleration. Gravity does not turn off. It's always that 9.8 meters per second squared down near the surface of the Earth. If the acceleration became 0 at that point, that would mean your velocity wouldn't be changing and things would get stuck there. You jump and you just kind of drift horizontally in space. And you need like somebody with a big hook to pull you down. So this is not how our universe operates. Now, before we go back to the problem, let's look at one more pattern here. Let's look at position. Okay, so if I rewrite this equation a little bit, it says, okay, the position I'm at as time goes by is going to be our starting height, which here I'm going to say is 0. So I'll make that term disappear. Plus our original speed times time, plus 1/2 acceleration times time squared. So let's alter that and put in the numbers. So 30 times time, and we're using 10 meters per second squared for acceleration. So 1/2 g is about 5 meters per second squared. So minus 5t squared. So let's run through the numbers here. And I might do the math a little rapidly, but let's take a look. So at 1 second, it's 30 times 1 minus 5 times 1 squared. So that's 30 minus 5, which is 25 meters. At 2 seconds, that's 30 times 2 minus 5 times 2 squared. That will be 40 meters. At 3 seconds, that's 30 times 3 minus 5 times 3 squared. So 90 minus 5 times 9, 90 minus 45 is 45. And that was our maximum height there. So it should be getting lower here on. Then 30 times 4 minus 5 times 4 squared, which is 40. And then 30 times 5 minus 5 times 5 squared, 150 minus 125 is 25. And then 30 times 6 minus 5 times 6 squared. And that is 180 minus 5 times 36, also 180, so that's 0. We see a symmetry here, both in the speeds and in the heights when we're accelerating at a constant rate. When you're at the same height, you're also at the same speed, but in the opposite direction. The motion, lousy catch there, the motion is the same backwards and forwards in this simple version here, where gravity is the only thing acting on the object. Okay. And those same speeds and same heights occur at equal times ahead and after the point where you reached the maximum, the point where it turned around. Okay, now that we've seen that pattern, and again, recognize that our speed at the point where we turn around is 0. Let's continue with the problem. So, let's take a look. We've got we know, let's see, we don't actually know the time of flight either, but I'm going to have us not bother to solve for that, but I'm going to note that we don't know it. Let's take a look at how we would approach this based on our older techniques. So we don't know the time. We also don't know the original velocity. But we know everything else. But every one of these, those are the two unknowns. So this means, though, that we could substitute in one of these equations for another. We could solve for the variable we don't care about, time, and substitute that equation into the other one to get an equation that will be able to help us solve for velocity. Let me show you what I mean. So if I take that top equation there, v final minus v0 equals acceleration times change in time, and divide both sides by acceleration, we're left with change in time is equal to the change in velocity divided by acceleration. Now we also had, let's say this equation here, that change in position equals original velocity times change in time plus half acceleration times change in time squared. So what we want to do is take this and put it in where we've got our times. So change in position is v0 times v final minus v0 over a plus a over 2 times v final minus v0 over a squared. Okay, so now we play with algebra. I can see here that we've got an a in the denominator in this first term and a 2, well, if we square the top there separately from the bottom. This power of a cancels with that. We have 2a on the bottom here, a on the bottom there. So let's give ourselves common denominators and multiply this by 2 over 2. So now we have delta x is 2v0 times vf minus v0 plus vf minus v0 squared all over 2a. Okay. And let's see. I'm going to erase our problem solving tips over here so we have a little more space to work. Okay, let's see. Let's multiply both sides by 2a and distribute this 2v0 and square that term there. So we've got 2a times delta x equals 2v0 times vf minus 2v0 times v0 plus this binomial squared. Algebra, you know that there's the FOIL method there. We can find out that's going to be the first term squared, v final squared, minus 2 times the product of each term, v0, v final, plus the second term squared. And we see that the terms that combine v0 and v final, we have positive 2v0 v final and a negative 2v0 v final. They cancel. And we have negative 2v0 squares here, but positive 1v0 squared there, which add together to equal negative v0 squared. So we're left with 2a delta x equals v final squared, this guy, minus v0 squared. This is our keeper equation. So I'm going to rewrite that in just a moment, and then we'll actually come back to the problem. Okay, so let's do that. I'm going to put our v final squared minus the original squared on the left side, though. Okay, so now we go back to our original problem where we're trying to find the original speed. This new equation, that's our only unknown. So we can go ahead and solve for that. The final squared minus the original squared equals 2a delta x. Speed at maximum height was 0, so that term drops. v0 squared is negative 2a delta x. v0 is square root plus or minus the square root of negative 2a delta x. when you take the square root, you've got the two, when you do this, you've got two solutions, the positive and the negative solution. Now we know that it's going to have to be the positive solution because we chose positive to be up. The negative solution would be referring to the velocity when you were back on your way down, but with the same other conditions we put in, the same change in height, the same acceleration. So you get back down to the original starting height, then you'll have the same speed. That's sort of what we saw in the table we generated before. So we'll just take the positive square root here and dump our numbers in. V0 is square root of -2 times -9.8 times 1.5. All right. I am not terrific with square roots in my head of non-whole numbers. So let's try this. So the negatives cancel, so that's 19.6 times 1.5 square, oops, 29.4, take the square root, 5.4 meters per second. And that's the speed of the jumper's center of mass. Their feet are going faster than that, which is why this looks different than maybe the sort of speed you would get for an Olympic 100-meter dash sprinter, which should be closer to like 11 meters per second at their max speed. But anyway, this gives us a good idea about what is like sort of our maximum launch speed for a person. Okay, so let's stick around for a little bit and try something spiffy. Back about 100 years ago, there's a series of pulp adventure fiction novels by Edgar Rice Burroughs. And he wrote a bunch of different adventure fiction novels. He's most famous for writing the Tarzan novels. But another series that he wrote about was called John Carter of Mars. He made a movie springing from those a few years ago. It didn't do well at the box office, that's why there aren't more of them. But the premise of the movie, the premise of the books is this. There's a old Civil War soldier who's become a cowboy who stares at Mars, who like finds a magic cave, stares at Mars one night, and then finds himself transported there. And since this is like 1900 or 1912 or something like that, and we didn't realize that Mars didn't have a breathable atmosphere, then it's fantasy Mars, where he can go around and there are other, intelligent creatures, and there's romance, and there's all sorts of adventure novel tropes. But G for Mars is not 9.8 meters per second squared. No, it's more like 3.4 meters per second squared. Because Mars is smaller and lower mass. So how's that affect your high jump? Well, let's say you've got, your adventure hero with Olympic class jumping. So your original speed is what we just found it to be for Olympic class high jumpers on Earth, 5.4 meters per second. And they're going to reach some maximum height of 0 meters per second. But now we want to know, what is that maximum height? Well, we look at our equations over here again, and we still don't know the time. Now we know our takeoff speed, but we don't know that maximum height. And so we can use the equation we just found to find the maximum height. So let's do it. So that's v final squared minus v original squared is 2a delta x. V final squared is 0. Delta x is negative v0 squared over 2a. That's negative 5.4 squared over 2 times negative 3.4. So what do we got? 5.4 squared divided by, the negatives cancel, so divided by 6.8 is 4.2, let's round it to 4.3 meters. That's above center of mass, so you're looking at a total of about like 5.8 meters above the ground. 5.8 meters, that's almost 2 stories high. That's the ability to leap over a small building in a single bound, which is more or less what the folks who invented Superman were thinking of, with our person from another planet arriving where gravity was stronger and having an ability to jump where there they would be able to jump normal heights scaled to us. Here, since our gravity is weaker, Superman can leap much higher. And John Carter was sort of like a partial model for Superman 30 years later. And that's it for this.